Who am I and why am I here? I swear I am not a cat. I got into InfoSec as a password cracker. Then, I'm a cryptography enthusiast, and about a decade ago, I was watching a tech YouTube channel, and they kept on being sponsored by a password manager, and I was like, maybe I should look at it. And sorry, I can hear myself. Sorry. I started finding all these bugs. It was the first time I actually code audited anything, and there was like a anyway. So there's like downgrade attacks and stuff like that, and then I looked at other ones, and they had similar bugs and whatnot. And basically, I decided how would I make one, and then this is basically that journey. I was on the password hashing competition panel, and I broke, I don't actually know how to say that. I assume it's like Latin, so it's like the Visa U. And then I broke delegation for the original version of Makwa, but that was fixed. So here's the agenda for today. Key stretching, and then password authenticated key exchanges. So key stretching, this is usually for passwords. So hashing, that would be for authentication. So when you log into a website, they hash your password, look it up in a database, and then see if it's right. And then password KDF. That's to generate a key, usually for like encryption or algorithms like PAKEs. There's also another thing that you can do with key stretching, which is fingerprints. One example is signals, safety numbers. They generate, it's a 30 decimal digit number, which is basically 100 bits, and they wanted to stretch it to 112. So why would you key stretch for passwords? That's basically what I'm going to be talking about. But Ashley Madison, there was a breach. bcrypt cost 12. Those are really, really good key stretched. They're really slow. It's 100, a little over 100 hashes per second that you can do on a GPU. So if you were to guess one password, such as password, against all the password hashes in the database, it would take 90 GPU hours to guess one. But they also stored salted case-insensitive MD5 hashes next to them. There were 15 million of those, and then when it was discovered by Sinosure Prime, 11 million of those were cracked in 10 days because MD5 is very fast, so then all they would have to do is run it, figure out what case those passwords were. So in those 10 days, 73% of those were broken. So there's different types of key stretching algorithms. Computationally hard, basically just how much work is done. So number of blocks of hashing that you do. There's parallel versus sequential. As an attacker, you only care about how much work was done. And as a defender, you only care about how long it takes. So if you have a computer with multiple cores and specific CPU instructions called SIMD, single instruction, multiple data, you can then run 100 hashes in parallel versus one that you would be able to do. So it would be harder in a shorter amount of time. Memory hard, the way that those are strong is the amount of memory that's being used limits how many threads on a GPU that you can be using. So as you use more memory, the GPU can't use as many threads. And also, how much bandwidth is consumed, because GPUs have a lot of bandwidth versus CPUs. Cache hard, the way that these are strung is instead of bandwidth, it's the number of transactions. So on a GPU, the bandwidth, the bus size is rather large. And with cache hard algorithm, you're only using a fraction of that. So you're reading like a 64-bit, randomly 64-bit integers, and then combining all those with a very fast operation like add and XOR. So here's some algorithms. Parallel PBKDF, I'll be talking about that later. PBKDF2. bcrypt, bscrypt, that's algorithm that I did a talk at B-Sides yesterday. Memory hard, Argon 2, that was the algorithm that was picked from the password hashing competition. Key stretching. So basically, if you're making a key stretching algorithm, if you follow these 3 steps, and there's the optional step for memory hard where you're doing lookups that are independent of the password. So you hash all the inputs, password, salt, whatnot. Then you do work with that seed. You generate work, a value called work, and then you use a KDF to then stretch it to whatever size you want. So if you don't follow, so these algorithms don't follow those 3 steps, and there were CVEs on them. These were, so when I came up with those 3 steps, that is very new in comparison to these algorithms. These are older. Technically, PBKDF2, that CV is because of an implementation bug. So key stretching bugs, bcrypt silently truncates to 72 bytes. And so this is code from the UK's government's police cyber alarm. I don't actually know what that is, but Paul Moore on Twitter tweeted about this. So basically, phash, that is 64 bytes. So it leaves only 8 bytes for your password. There's a simple fix. If you actually hash all of that along with the password, then this is actually close to what you should be doing with bcrypt. You want to hash the password with HMAC. So you can have a pepper as the key, and then the message being the password, and then put that in. And then you want to have ASCII encoding of it. So even if you do follow all the steps, there still can be bugs that happen. This was with Bouncy Hassle. It only checks the first occurrences of those characters, and a few of them are at the beginning, and there's a probability that you get an unlucky hash where any password would match. So I calculated those probabilities when the bug came out. I haven't actually double-checked, but I'm pretty sure they're right. So how to do key stretching? So these are the 3 steps. I've removed the optional step. And you might be looking at do work and thinking, there's a lot missing there. So how to draw an owl meme, So this is PBKDF2. There's actually 2 issues with it, according to the 3 steps. So if you don't do HMAC init and HMAC finish, if you were to just do HMAC where all the HMAC finishes are, as a defender, you'd be doing twice as much work. But also, if someone enters a really, really long password, you have to hash that every time, and it'll be a DOS. One of the CVEs was basically that. Also, the red boxes, those are independently generated. So if you ask for more output from PBKDF2, you're doing more and more work. But you can use that as, you can use that footgun for an algorithm. This is something that I came up with, parallel PBKDF2. Basically, you just ask for a large output, and then you XOR all those blocks together. Then You put that into PBKDF2 to stretch it to whatever length you want. NIST should like fast track some, and PBKDF3 that is something like that, because currently they suggest PBKDF2 or balloon hashing, but balloon hashing doesn't actually have a spec. Like it's just an idea sort of thing. So minimum password hashing settings. You want to make sure that an attacker gets less than 10,000 guesses per second per GPU. Jeremy Gosney is the one that was quoted saying this, that it was after a breach, and the password hashes were such that they were less than 10,000 per the fastest GPU at the time, and he said that that was proper slow. I then used that and then changed the definition of GPU to mean the best for password cracking. And so maximums, these are very dependent on what your hardware is. So if you basically don't want it to take too much time or too much memory, and if you're doing server authentication, like hashing, you want to make sure that your throughput is what you want. And since those are all dependent on your hardware, I'm just going to talk about minimums because it's easier to give minimums. So bcrypt, as I said, this was I did a talk at B-Sides LV yesterday. So those are the minimums. These are actually extremely fast. You can go way higher. These are like runtimes of milliseconds. So the 1.9 million in the, I should have highlighted that, whatever. So basically, in general, you want to use the highest cache level per core. And then for number of iterations, T, that's based on how many memory transactions a current GPU gets. So bcrypt minimum settings are very simple, cost 9. Technically, well, because the way bcrypt works with their costs, it's exponential. So it's technically like 8.1, but you have to put in an integer. The link at the bottom of the screen, that is my webpage. I will be updating that with current recommendations. So Argon 2, they had an RFC. The people that made Argon 2 put out an RFC. And so those are the settings that they gave. Basically, 2 gigs, 1 iteration, 64 meg, 3 iteration, very similar. Just kidding. Those are wildly different. The password manager that I use, KeyPass, they don't even allow you to do 2 gigs. So these are my minimums. These are based on the memory bandwidth of current GPUs. Basically, there aren't any good benchmarks for it, for password cracking. So if you look at the general formulas, the alpha variable, that is the percentage of memory bandwidth that you can actually consume, and that depends on how much memory, the memory setting. It's assumed that around 64 megs-ish, then that will start dropping as you double memory. The speed of a GPU will be cut in quarter because it's doing twice as much work with half as many threads. So scrypt minimums, same thing. It was based off of memory bandwidth. So you don't have to answer. Just think. So PBKDF2 pulse settings. What do you think is like a high number? Like a good number and what you think industry standards would be. Well, here's my minimums. So it depends on what algorithm you're actually, hashing algorithm you're using. So SHA-1 is very fast on a GPU, so that's higher. Technically, Blake 512 would be the best algorithm to use because there's internal parallelism. So as a defender, you can use SIMD instructions, single instruction, multiple data. So it will be faster, but faster as a defender for the same strength as others. So parallel PBKDF2, it's a simple thing, cost 3, cost 1. Each cost is equivalent to over 100,000 iterations. So password authenticated key exchanges. So you can use these for password authentication. So when you're logging into a website, instead of giving your password over, you do this key exchange. Then there were a few years ago, a bunch of companies found out that they were accidentally logging passwords. So if they switched to a password KDF, PAKE, then even if they did log all those messages, there wouldn't be anything important in them. So you can also use PAKEs to establish a encrypted tunnel. You can use Magic Wormhole for sending files or fighting phone spoofing. So you might be, if you've heard of Scram, maybe not. The problem with Scram is you have to be on an encrypted channel because anyone that sees those messages, if they see a successful login, those messages are equivalent to a password hash. So in the case of logging, you'd be logging password hashes. So types of PAKEs. Balance, those are peer-to-peer. So a person types in a password on one side, someone else types a password on the other. Then there's augmented, APAKE. Those are client-server. Do not call these symmetric, asymmetric. One reason is there's asymmetric and symmetric cryptography, but also it implies that there's only two. So two different types of PAKEs. Doubly augmented, this was, there's a long email from Mike Hamburg where at the end he, just like in a really short sentence, mentions that it could be doubly augmented. And a few years, he said he didn't know a good way of what that could be used for. A few years later, I figured out the perfect match for it, which is Wi-Fi. So basically, your doorbell and your access point. Your doorbell would be a device that has basically, you don't want someone to break into your doorbell and then be able to use the information stored on it to spin up an AP and then attack your network. With the doubly augmented PAKE, the doorbell wouldn't have any information necessary to make an access point. Then identity PAKE, this is basically everyone has an identity, roles, and permissions and stuff, and a good fit for that is IoT. So the hierarchy of PAKEs, basically if you need a balanced PAKE, you could technically use any of these, but they're more work. But if you needed something that was a doubly augmented PAKE, then you could either use that or an identity PAKE, but nothing else. So balanced and identity PAKEs, those are more peer-to-peer, or could be, like in the case of IoT where two devices are talking to each other. Then augmented and doubly augmented, those are more client-server. The top two are basically human is involved, and then the bottom two, those are where two computers can be talking to each other, or devices. So how do PAKEs work? So this is standard Diffie-Hellman. You have Alice and Bob talking to each other, and so they both generate a random private key, then do scalar point multiplication to create a public key, then they exchange them, and then they apply their private key to the other's public key, and then they get SA, SB. Those should be the same unless there was someone man-in-the-middling this connection. And so what you can do with PAKEs is you can hide the ephemeral keys that you're exchanging. So one way to do that is you take the password, you hash it, then you put it through this function called hash to curve. What that does is it's different than scalar point multiplication, where when you give it the hash of the password, you don't know the private key, basically. So it generates this point, the password point, I'll call it. And so when you generate your ephemeral key, you just add that point to your ephemeral key, and then exchange that. Then you remove it by subtraction, and then apply your private key. And then SA and SB should be the same, assuming the password is correct. Another method is hiding the generator. So you do the same thing with the hash to curve thing, but instead of using the standard generator, you use the password point as the generator. So the patent expired in 2017, so we can now actually use this, which is good, because this is the easiest method, because it's just Diffie-Hellman, and you don't need to rely on password addition and subtraction. So this is recent, more recent. So hiding the salt with an OPRF, oblivious pseudorandom function. So basically, you do the same thing where you do hash to curve with your password and stuff. Then you blind it with a random value. Then you send that over to the server. They apply the salt like a private key. Then they send that back to you, and then you unblind it by scalar point, or scalar invert, and then scalar point multiplication. And basically, the blind salt is what I call it, equals the salt times the password point. And the server doesn't learn what that point is, and you don't learn what the salt is. So how do these PAKEs work? Basically, it's basically like different types of key exchanges. N means no static key. K is the other party knows what the static key is, what your static key is. The first letter is the initiator, and the second is the receiver. So balanced, so all the arrows that will be on these slides are Diffie-Hellman. So ephemeral key to ephemeral key for balanced, static key ephemeral to ephemeral, noise KN, doubly augmented. Anyway, so 3DH, So these are PAKE algorithms. The way that they're colored is by what they're hiding. So the ones with red stars next to them, those also hide the salt, like OPAKE does. So the identity PAKEs, those they're not colored because those actually just use a balance PAKE, so their color would come from, or like what they hide comes from what balance PAKE that you use. so there was a paper that made chip and crisp, where they said that crisp protected the salt. Basically, yeah, so basically, instead of protecting it before you run the password KDF, it was that after that, where you had to run it was a more expensive key exchange that you had to run each time. So I came up with fry, because chip, crisp, fry. Basically, it's just chip, but has an OPRF. And it does mess with the way that their setup works. It's kind of a joke. But, so PAKE properties, forward secrecy, that's basically every single PAKE has that. Prevent pre-computation, that's the protecting the salt. Can you turn the music down? Thank you. So pre-computation, basically what that does is it protects the salt so that when you're, so it prevents this attack where you run through the password KDF a bunch of times with different passwords before you break into the server. Then when you actually break into the server, you can then check all those passwords near instantly or instantly. So crisp slightly protects it. The key exchange is fairly expensive at being about like 4 milliseconds, which isn't actually a good property because your IoT devices would have to run that algorithm every time. But secure registration, basically when you register, if you're being man-in-the-middled, since there's no like pre-shared key between you and the server, someone can just come in and then man-in-the-middle, grab that, all the information, and then later, when you try and go to the actual server, you would notice that it doesn't work. Quantum annoying, this is a term that I came up with. There was a paper that tried to formally define it, and they did a talk at PQ Crypto. So quantum annoying, what this is you have to you have to solve a DLP for every password guess. So so when you see a successful PAKE exchange, you then capture all the packets. If you had a quantum computer, you'd have to solve one DLP for every password guess, basically. Fragile, what that is all the security of the algorithm depends on static Diffie-Hellman, a static Diffie-Hellman oracle. And number of trips, 3 versus 4. Obviously, 3 is better. But when I coined the term, I didn't actually know that anyone knew about this property. So Speak, when I was reading the Speak paper, I noticed this quote. I'm not going to read it, but then they referenced the EKE paper that basically said the same thing. Anyway, so PAKE properties by algorithm. So quantum annoying, that is a very good property to have, for future of PAKEs, assuming if a quantum computer ever does come out, these would a quantum annoying PAKE would be basically a stopgap between when quantum computers come out and when you have to change algorithms to a post-quantum PAKE. And for the case of opaque, because it's fragile, as soon as quantum computers come out, every single password can be cracked on classical computers with GPUs and stuff. CPACE being a balanced PAKE, you don't have pre-computation or secure registration because there isn't any. So the cost of BS-speak versus opaque 3DH, basically, oh, hey, you can see green. All right, so green, those are just the extra operations. So they're fairly similar in speeds. Basically, every time you do a scalar point multiplication, you then have to do a field invert, which is a little expensive, but not as much as a scalar point multiplication. But the nice thing is you can actually combine multiple of these field inverts into one. That's so. If you were wondering why there were less i's than scalar point multiplication. Oh, and I separated them from OPRF and the key exchange, PAKE. Anyway, so if you are going to implement any PAKE, you should use an API like this, where you initialize all the information, get the secret and whatnot, and then return a message, or maybe you're supposed to be the one receiving the first message, so there wouldn't be a message. And then when you receive a message, you send it into a function that then returns the next message, if there is a next message, and a status. The reason for this is I've seen a lot of implementations of SRP 6A where they just say calculate A and calculate M1, and they're like, oh, the developer will know what that means. So this way, it's very hard to misuse the API. And then you would want to be able to get the secret stored, the server stored secret for augmented PAKEs. And then also, if you're going to do authentication and encryption with a password, you would want a API function that returns a key based on the password. This is so that you only run the password KDF once and generate a key for the PAKE and a key for encryption. So cheat sheet. These are all the correct answers according to me. So BS-speak, double BS-speak, those are actually algorithms that I came up with. Basically, it's just hide the generator with hiding the salt and noise KN and then noise KK, well, 3DH. And then use chip if you need an identity PAKE. So balanced PAKEs don't need key stretching. And then bcrypt minimums are there. I just remembered that I forgot to mention balanced PAKEs and Wi-Fi. So the Wi-Fi Alliance, they picked a PAKE that was actually known to be broken at the time. That PAKE is a balanced PAKE, and then they actually store the password on the access point and device instead of using a doubly augmented PAKE. So agenda, I'm good. OK, so questions? I do have bonus slides, and references, but if anyone has questions.
There are no questions from the virtual audience at this time. If a member of the in-person audience has a question, please step up to the mic.
Do you want bonus slides? OK. All right, so the secure registration for the server checks, verifies that so the entire top half of the algorithm is, I have a gist for this on GitHub. But basically, run through the PAKE, and then this is at the point where the server checks the client verifier. It generates another verifier, a session key. That session key encrypts reg and regmax. So reg is the ephemeral private key that was used during registration, and then regmax is a MAC. Did I say max? MAC. A MAC of the public key reg. So the server encrypts that with the session, sends that over. Then the client checks to see the server's verifier is correct. Then it creates the session key. Then it decrypts the private key during the ephemeral private key during registration, and the MAC key. Oh, all right. So the MAC key is generated from the password. So when you run the password KDF, you output a bunch of stuff, and one of those things is the MAC key. So the MAC key is then used to sign the public key, or not sign, hash the public key, that. So if that fails, then that means that you were man-in-the-middled during registration and no longer being man-in-the-middle. So you can detect when that happened. So bcrypt. So these are all the fun slides from my talk. But first, one info slide. So so the way that it worked was, so cache hard algorithms, they get their cache hardness from small random lookups in memory, or cache. And then you do every other operation is add XOR. So, and I went with 2 S boxes like that. So the interesting thing that I did with that is these S boxes are overlapping. So other algorithms that are cache hard, the S boxes need to be a nice binary number. So do these, but since they're overlapping, you can get whatever sizes, you can get exotic sizes from these S boxes. So this was a benchmark that I did on my laptop. The settings are such that they're all the same for a GPU attacker. Since bcrypt is the one where you don't have much leeway because it's, this was for cost 9, and the next one is like twice as hard. Or so as an attacker, all of these algorithms with the settings, those are all considered the same to them. They wouldn't care. But as a defender, you can spend 4 milliseconds on bcrypt or almost 800 milliseconds on PBKDF2 SHA-256. So this is the speeds at, this is a desktop computer that I ran the benchmark on with different number of threads. So this is for minimum settings. And it basically took 1 to 2 milliseconds, which is really, really fast. So these are equivalent speeds for cost 15. And you can get these in under 100 milliseconds. If you're familiar with bcrypt, cost 15 is ridiculously high and takes a very long time. Clamp, scalar, invert, so you do some stuff, and then, yep. Oh, okay, it said 30 seconds. Okay, thanks.